Hello, so this is problem 2320, count number of ways to place houses. Let's start with the problem. The problem is we have a road which has two sides. Each side has n plots where we can place the house on the plot. The, the requirement here is we must not place two houses adjacent to each other on the same side of the street. So when it is on the same side, you cannot be a neighbor there. Okay? And then we need to return it with modulo 10 to power of 9 plus 7 just because the number can be very large. And it can cause overflow if depends on your variables and your programming language. The overflow is different. And note that if the house is placed on ith plot on one side, a house can also be placed on the ith plot on the other side. It means that there is no restriction when it is when we consider the two different sides. Okay. An example: when there is only one plot at one side, there are four possibilities. One is we don't place any house. Second is we place house at one side. The third one is we place house on the other side. And finally, we place one house in each side. When there are two houses, this is the example, there are 9 possibilities. Empty, one house, one house, one house here, two houses like this, two houses like that, two houses like this. Okay, and in total there are 9 possibilities. And we know that n can be very large, so that's why they reminded us to do the modulo. So let's start with the tactic here. To build the tactic, we need to start with the examples and see what we can do, and then try to explore it by running several things manually. N equal to 1, we got 4 as the result, right? Result is 4. N equal to 2, we got the result is 9. Okay, how about n equal to 3? Let's look at one side. Everything empty, that's one possibilities. And then when there are two houses, 3 means like this, right? When there are two houses, there is one. When there is only one houses, we have 3 possibilities. When there is two houses, we only have 1 possibilities. 3 houses is already impossible. So in total, we have 5 possibilities if we consider one side. Now, if we consider the other side, obviously the other side have the same thing and there is no relationship between each other. It means it's just the result become one side square. Why it is like that? Imagine when we have this at one side we have the houses here, it means the other side can have all these combination houses. So that's 5 combination. Then when we have the houses like this at one side, we have another 5. So for each possibility at one side, we have those 5 things possible. So in total, this has 5 possibility. So it becomes 5 times 5. That's why it becomes squared. Okay. So now we know that relationship. We know this one has the value of 25. How about n equal to 4? One side, when we have 4, when it is empty, we will have 1. When we have 1 houses, we can place it on the 4 plots. We have 2 houses, it become 1, 2, 3. Right? This is the third one. Okay? And when we have 3 houses, it's impossible to satisfy the requirements that no houses at the same site adjacent with each other. So in total, we have 8 here. And the result is 8 squared, 64. Now we look at here, we can see some pattern here. The pattern at the one side. If we calculate the one side here, it means there are 2, there are 3. This one, I'll just copy it here so that we can line it up. And we can see there is a pattern here, that 5 is 3 plus 2, and 8 is 5 plus 3. So if you remember, if you ever do some IQ test, there is this kind of problem where you have to guess what is the next numbers. So you can see here, we see a pattern here. The pattern here is that whatever the number now is a recurring things, it's become n minus 1 plus recur n minus 2 when we are looking at n, right? Because 5 is 3 plus 2 and 8 is 5 plus 3. To make us more confident with this guess, we try the n5. When we try n5, we know that the one side is, when it is empty, it's 1. When we have one houses, there are 5 possibility. 2 houses, 1, 2, 3, and then 5, 4, 6, 5, sorry. This one already. And when we have this, we already tried this. This one not yet. So 6. This one we already have. So that's when we have 2 houses. When we have 3 houses, it become only 1, which is this one. Yeah. When we have 4 houses, it's already impossible. In total, this is 6. Wait. 1 plus. When we have 4 houses, yeah, it's impossible. When we have 3 houses, like this. Well, when we have 2 houses, what was it? 1, right? 2, 3. 4, 5. 6. Yeah, 6, correct. So this one becomes 6 plus 1, so 13. 13. So does 13 is 5 plus 8? Yes, it is. Then we got the relationship here. I forget the name of this. I think Fibonacci. Maybe I'm wrong, but basically this is the relationship. And then after we got that one-side relationship, we just need to square it to get our result. Now that we know about this, we can just do our memoization, because this is a very famous problem in algorithm. So I just forget what the name is. Basically, we just need to do this, and then the relationship will be minus 1 plus recur and minus 2, and there is termination condition. When n is just 1, we return 2. If n is 2, we return 3. Basically this one, okay? And then after that, we need to do memoization to make this, what you call that, efficient. Result is this, and then we just need to remember to do the modulo, because it can be pretty big. Modulo just now was power of 9 plus 7. 1, 2, 3, 1, 2, 3, 1, 2, 3. That's 9 plus 7. So we do the modulo here. Okay, and we return this as the result. Because we already memorized it, if ever that n in memo, we just return it directly, what we already calculated. And as the final result, we do the recur, giving the n, and we do the square. Not to forget, we need to modulo it, and we return that. Let's try 4949. Sounds correct. Submit. Accepted. It's performant enough. Good. Now the time complexity. For time complexity, we need to draw things out so that it is easier for us to understand the reason why that's the case. So if you notice the key point here, I mean the termination condition will make it a little bit skewed in our first few examples, but in the big O is when numbers are quite big. What is significant is this one, right? In order to understand the time complexity here, we need to start from when we don't have the optimization, when we don't have the memoization, what happened? After we have it, what happened? Okay, so when we look at here, whenever there is an n, what happened is it will be divided into two possibilities, right? The possibilities one and the other possibilities. And how many are we going to have these things? It depends of the n. So the height of the tree is actually the n. It's a linear relationship with the n. The more the n, if n is increasing by 1, the height of the tree is increasing by 1. Okay? So the more n, the more is the height. And for each height, it will have the relationship to 2 of its previous value, which for its previous value, it has the relationship of its other 2 previous value. Like this. Okay, so what it means? Remember that this means that for each increment of n, it it will increasing by 2 to the power of n. And the number of nodes here, if you remember about the trees, is basically about 2 to the power of n divided by 2, if I'm not wrong. So in the big O, we can see that if we don't do any optimization, more or less it's become 2 to the power of n. Not 2 times n, 2 to the power of n. Okay. Now what happened when we do memoization? When we do memoization, actually, let's imagine this. If it is 5, then it's become 4 and 3. And this become 3 and 2, 2 and 1. Then of course this become 2 and 1. Okay, so when we have memoization here, when we traverse that first search, we already got everything. Then the rest we just need to memorize from whatever is in the memo. It means when we have the memoization, we only have to go through one side, the height of this. It means, what is the height just now? The height is the n. So the time complexity become big O n. That's it about the time complexity. Thank you for watching.